We are today going to finish that chapter on graphing the trig functions. We're going to look at tangent, cotangent, secant, and cosecant. And then we'll get started on a new chapter. I also have a new handout for you. Everybody got their tests and problem set back. You can earn points back on the test. If you go onto Canvas and click on the link for test number 1, you should see a PDF of your assigned problem, and that's due a week from today. We have recitation today, and there'll be a practice quiz to get us ready for the quiz on Thursday. The Thursday's quiz will cover the graphing, but I'm just going to restrict it to the sine and cosine functions, and then integer exponents, which will be a little bit of review, kind of covering some ground that we are already hopefully familiar with from last semester, and then the rest of that chapter is sort of working with rational exponents and radicals and all that fun stuff.
Do you want me to let the air go then?
Okay, so does anybody have any questions they'd like to ask before we get started? Okay, all right. So the last bit of new material we did was graphing sine and cosine. So now we're going to start off working on graphing the tangent function. So, these values that I plugged into, or that you see in the first, I guess it's the second column. So I've got our values, our convenient values that we have on the in the first quadrant, or I guess in the fourth and first quadrant. I just got these values by using the fact that tangent is equal to sine divided by cosine. So I took like the sine coordinate and divided by the cosine coordinate. So a negative pi over 3, which is the same as 5 pi over 3 here. I took negative root 3 over 2 and divided it by a half, and that gives us negative root 3. And I just selected some nice convenient values here. At 0, tangent of 0 is 0 because sine of 0 is 0. Kind of use that point to anchor down the graph. And then kind of branching out from here, negative pi over 4 is at, this is supposed to be, I wrote negative pi over 2 twice. Sorry about that. That's supposed to be a negative pi over 4 there in between negative pi over 6 and negative pi over 2. So at negative pi over 4, we're at negative 1. At negative pi over 6, we're at negative 1 over root 3, which is approximately negative 0.577, so maybe a little bit below the half, the negative half. Negative pi over 3, we're at negative root 3, which is negative 1.73, so, maybe about here. And then over here at negative pi over 2, there's just a star. So, what does that mean? And in fact, if we just think about trying to compute it, right? If I wanted to find tangent of negative pi over 2, that's sine of negative pi over 2 over cosine negative pi over 2. So sine of negative pi over 2, that's the bottom of the circle, right? What's sine equal to there? I guess it's sort of covered up a little bit by my taskbar.
Is that your wallpaper?
That's my wallpaper, yeah. So we're at the bottom of the circle. What's sine going to be? Close. We're at the bottom of the circle?
0.
Nope. -1. Yeah. So -1 on top. What's cosine at negative pi over 2? What's cosine at the bottom of the circle? 0. That's 0, right? Okay. So this is why we have a little star here in that entry. Tangent of negative pi over 2 is not defined. Also true for positive pi over 2, right? Any place where cosine is 0, the tangent function is not defined. Now here's a cool thing that happens, right? As we get close to negative pi over 2, imagine I'm just sort of inching closer and closer and closer to that value. The sine function is just getting close to 1, so it's kind of stabilizing. It's not doing much. The cosine function is getting tiny. So imagine that the sine function is just fixed at -1 for a second. Like it's not moving very much, so it's not affecting the behavior that much. So I take this value -1 and I'm dividing it by numbers that get really small. Like by 1/10, by 100. What's 1 divided by 100? If I have 1 and I divide it by 1/100th, what do we get? Say that again. 100. What's 1 divided by 1/1000th? What's 1 divided by 1/1,000,000th? Okay, so as these values, of course now it's negative, right? Because I guess the top is actually -1, but as I just get kind of creep closer and closer to negative pi over 2, these values just blow up in the negative direction. So at x equals negative pi over 2, we have what we call a vertical asymptote. And an asymptote is a line that a graph approaches. So I know that as the graph, as x approaches this dotted line, it just gets closer. Closer and closer and closer. Vertical asymptotes can never be crossed, right? Like, you know, we might see some stuff. We definitely will see some stuff if you take calculus. We might see some stuff later on talking about horizontal asymptotes, which is a similar kind of thing. It's a line that a graph approaches. Horizontal asymptotes can actually be kind of crossed, right? They just talk about the behavior as x gets large. Vertical asymptotes can never be crossed because they represent a value that we just can never plug in. Like it's not in what we call the domain of the function, right? Not allowed to plug it in. So that's what's happening here, and then we have a couple other points here, and then it moves into the point 0, 0 goes to the origin. Oops. And then on the other side, we get kind of the same type of behavior. So at pi over 6, we're at 0.577. Pi over 4, we're at 1. Pi over 3, 1.73. Oops, hold on a second. I have to kind of adjust a little bit the behavior. So again, at pi over 2, positive pi over 2, that's the top of the circle. Cosine is still 0. So that function's going to blow up, but of course sine is approaching +1, so it blows up in the positive direction. And then it kind of goes through these points. And then I want to just sort of connect these. Right, we have a nice smooth curve. It looks something like this. This is generally true anytime you have a function and there's a value that would make you divide by 0. There are certain circumstances where it doesn't cause it to exactly blow up, but most of the time, unless the value makes both the top and bottom 0, right? If it makes the bottom 0 and the top not 0, it will blow up. That's what it does. We're working on the last handout that we started. So there's our graph for tan of x. when we multiply a function by a number, all we're going to do to get those values is just double, right? We're just, whatever our tan x values are here, we're going to double them. So it still blows up at the same spots, right? It just blows up maybe a little bit faster. And so if I double each of these, we still have that blows up there. So we have negative 2 root 3, which is about 3.46. And then this is negative 2. So here we have negative 2 over root 3. And that is about 1.15. 2 times 0 is still 0. And then we get the same values on the other side, just positive. So about approximately 1.15, positive 2 root 3, or approximately, oh, that was a negative and that was a negative, positive 3.46. And then again, it still blows up at positive pi over 2. So they go through the same point 0, 0. And then let's see what happens. Negative, let's see, at negative pi over 6, we're at negative 1.15. At negative pi over 4, we're at negative 2. And then negative 3.46, so just about the 0, or the negative 3.5. At pi over 6, we're at 1.15. So there, at pi over 4, we're at positive 2. At pi over 3, pretty close to 3.5. And then again, it still blows up. So we have this behavior. Same kind of behavior. All it did, it seems, is if you take the black graph, what you do to the black graph to obtain the blue one, you just kind of like stretch it out a little bit. All right? And we do this one more time and graph 1/2 tan x. I'm just going to take the values in the second column and cut them in half. And I'll do this one in green. So we have minus root 3 over 2, which is approximately negative 0.866. Here we have negative 1/2. Let's see, negative 1 over 2 root 3. Which is about negative 0.289. Of course, 1/2 of 0 is still 0. And then we have the same values reflected in the positive. So approximately 0.289, and then 1/2, and then approximately 0.866. And then we still have the asymptotes. So if we plot these, let's see, negative 0.866. Let's see, at negative pi over 4, we're at 1/2. Oh, whoops, I just plotted the wrong point. Give me 1 second, sorry. At 0, we're at 0. Now I'm going to move out in the negative direction first. So negative 0.289, that's better. And then negative 1/2, which is about there. And negative 0.866, which is about there. A little shy of negative 1. And then the same values kind of reflected in the other direction. So 0.289, 1/2, and then 0.866. We get the same general behavior, the same type of curve. Right, and that's, the green curve can be obtained from the black curve if you just sort of squish it down, kind of compress it. And that's generally what, when you take any function and you multiply it by a number, let's say you have a graph of y equals f of x, right? If you just multiply it by a constant out in front, it'll have that effect of either like kind of stretching it out or compressing it vertically. If you multiply it by a negative, it would also flip it around and kind of reflect it across the x-axis. But that's the basic behavior of a tangent graph. Sine over cosine. We could sort of see why we get these. This is just one period of the tangent function. It'll repeat itself. In fact, the period of a tangent function is pi, not 2 pi. If we repeated this process over and over again, we would get this same behavior. Right, so we graphed this curve, right, from minus pi over 2 to pi over 2. But it'll just kind of keep repeating from pi over 2 to 3 pi over 2 and 3 pi over 2 to 5 pi over 2. So it has a period of pi, and we can, if we wanted to adjust the period, we would do the same thing we would do with the sine and the cosine. I'd throw in a factor in front of the x, like inside the tangent function. We get the same type of behavior for cotan. So this was sine over cosine, right? And these asymptotes here, where it kind of blows up, correspond to values that make us divide by 0, where cosine is equal to 0. If we did the same thing, went through the same process for the cotan function, we would get the same type of behavior, but cotan is the reciprocal, so it's cosine over sine. And so we get those asymptotes where sine is equal to 0. So at the multiples of pi, at 0, at pi, at 2 pi, at 3 pi. And that's what we have, that's what we're looking at in the bottom part of this page. So if we just sort of look at this period from 0 to pi, it blows up in the positive direction when it approaches 0. That kind of makes sense because this is the first quadrant, right? So sine and cosine are both positive there. So if it's going to blow up as sine approaches 0, it's going to do so in the positive direction. From pi over 2 to pi, that's in the second quadrant. Sine is positive, cosine is negative. So cotan has to be negative here, right? We have a negative divided by a positive. And so as it approaches pi, it's going to blow up in the negative direction. Same kind of behavior, but just kind of flipped a little bit, right? When we graph cotan, which also has a period of pi, we graph it from 0 to pi because that's what gives us one nice smooth period that's not broken up across an asymptote. When we graph tangent, that period we graph from negative pi over 2 to pi over 2 because that's what gives us one nice smooth curve that isn't broken up by an asymptote. We can, as I mentioned before, adjust the period. Now, because the period of tangent and cotangent is pi and not 2 pi, then if I'm looking at tan of bx plus c, for example, this is all true for cotan as well. But if I'm looking at tangent of bx plus c, I still turn to that coefficient on x to tell me how to find the period, but this time it's just pi over b instead of 2 pi over b. And the phase shift is still the c over b units. We still do that thing where we factor out the b and we still interpret that value, right? We still just grab the phase shift from taking this value after we factored out that b. And the rule is the same as far as the direction. If it's a positive, if it's a plus a constant, it goes to the left. If it's minus a constant, it goes to the right. So we could, real quick, just kind of sketch a graph of this function. Or maybe not super quick, we can take our time and enjoy it. The first thing I'm going to do is rewrite this by factoring out the 2. What goes here? What do I multiply by 2 to get pi over 4? Pi over 8. What's the period? Pi over 2. Right, we're just taking pi and dividing it by that coefficient. And then the phase shift?
Pi over 8 to the right.
Yeah. Great. So what I'm going to do to sketch this is what we did with the sines and cosines, and that is I'm going to first just sketch it without the phase shift, and then I'll kind of push everything over. You notice we don't have, we don't mark down an amplitude for these graphs because there is no maximum displacement from an equilibrium, right? These things blow up. However, I do have like one point in particular that I almost think of as an amplitude, but I'm not going to call it that because that would be the wrong word. But if we look back at the first thing we did, right? I'm going to go back a couple pages. Let's look at these three graphs, and in particular, pi over 4, tangent's equal to 1, right? Tangent of pi over 4 is 1, tangent of negative pi over 4 is negative 1. I use this as my sort of single anchor, and it's not really an amplitude, but it's sort of the thing that I use like to kind of give me that anchor point. I know that tangent goes through the origin, and then if I have a coefficient in front, that just tells me where I'm at pi over 4, or at this sort of point where sine and cosine are equal. And then I often don't bother with the pi over 6 and pi over 3 like these other two. I just do like where does it cross, where does it hit its 1, or whatever that coefficient is in front of the tangent, and then do the same thing on the other side, and then where are the asymptotes. So if we do that here, the coefficient in front is just, in this function, is just 1. So at that value, where tangent's equal to 1, that's just as high as it'll go. And let's see, the period is pi over 2. So, and this is the tangent. So this is the one where I'm going to go half of that period to the left and half that period to the right. So I'm going to start off negative pi over 4 to pi over 4. Hold on, I'm going to adjust this a little bit because I need to leave some space for a phase shift. Okay, so this is for the graph without a phase shift. This is where the asymptotes will be. And then the halfway mark between the two tells me where it hits this coefficient, which is in our case just 1. So 1, negative 1. So here it is. I'm going to do this one in gray, I think. Here it is without the phase shift. And then what I want to do is just push this whole thing over by pi over 8 units. So I'm pushing over this asymptote, pushing over this asymptote. So that'll be pi over 4 plus pi over 8 is 3 pi over 8. And then I'm just moving over each of these points. And there's our graph. So there's like 3 points. I plot 3 points, like where it goes through the origin or whatever point that is, right? If there's a phase shift. I plot, at the halfway, I've got my 2 asymptotes, and then halfway to each asymptote tells me where I hit 1, or whatever that coefficient is, and negative 1. So I plot 3 points, I plot the asymptotes, I sketch, dotted line asymptotes, and then I just kind of draw the curve so that it fits in between. And the gray one was just tangent of 2x. No phase shift. We'll do one more. We're going to do 2 cotan of x over 2. So notice there's no phase shift here. I could tell because I'm not adding or subtracting anything inside the parentheses. What is the period? No. Pi, because, so what we want to do is take pi and divide it by the coefficient on x. What is the coefficient on x? No?
So 1/2 is the coefficient.
Yeah, right? Dividing x by 2 is the same as multiplying by a half. So our period is, in fact, 2 pi. And there is no phase shift here. Now this is the cotan. So cotan function, we're going to graph it from 0 to the end of its period. So we're going to graph it from 0 to 2 pi. So here's pi. In the middle, right, from 0 to 2 pi, that means that the y-axis and 2 pi, those are our asymptotes. Halfway in between those two is where cotan is 0. And then at the quarter marks here is where it hits its, I don't know, I don't want to call it amplitude, but like this value in front, that coefficient in front of the function. So pi over 2, 3 pi over 2. And that value is 2. So there's a 2, here it is a negative 2. And then we draw the cotan curve. Fun. So we'll move on now to talking about the secant and cosecant functions. We'll do secant, we'll do cosecant first. These ones are actually pretty simple. If I'm going to graph a secant and cosecant, the first thing I do is I graph its reciprocal function. So cosecant is 1 over sine. So the first thing I'll do is I'll sketch it lightly, like in gray or as a dotted line, just what the sine function is. We've been doing that for a while. So sine of x has a period of 2 pi, right? And so there's 2 pi, here's pi, pi over 2, 3 pi over 2. Has an amplitude of 1. Now I got to leave ample room on either side of the amplitude, so I'm not marking 1 at the very top. I need to leave some space. And its sine starts at 0, and it's positive sine, so it starts at 0 and goes up. So something like this. I feel like I can do better. Hold on. I know I can do better. Okay, It's fine. Just imagine that this point is perfect, okay? I could just move the pi over. Yeah, I feel like if I do... Well, actually, you know what? I'm going to do it. Ah! Okay, you know what? That's where I'm at. You know what? I'm going to be okay. Everything will be fine. Everything's fine. Okay. So there's my sine curve. So think of it now as you were graphing cosecant, but just think I'm graphing 1 over sine. The numerator is always 1. When sine is equal to 1, what's 1 over sine equal to? 1. And if it's negative 1, 1 over negative 1 is negative 1. So that means up here at the peak, cosecant takes on the same value. Down here at the valley, cosecant takes on the same value. Okay. So far we're doing really good. We have 2 points on our cosecant. Now, look. Sine is equal to 0 at some spots, yeah? So it's at 0 when x is 0. It's at 0 when x is pi. Imagine that I'm getting closer and closer to pi, right? In the x values. The numerator stays at 1, but sine is getting really close to 0. What happens to 1 over sine? Say that again? It starts getting bigger and bigger, like we saw with the tangent, right? The first thing we said was imagine with tangent that sine is just fixed at 1, and like what happens if we just divide by. This one is fixed at 1, right? That's exactly what this is. The numerator's fixed at 1, the denominator's getting close to 0. That means it's going to blow up. So I have asymptotes at any value that makes sine equal to 0. So that means that the y-axis, x equals pi and x equals 2 pi are asymptotes. Okay, now graphing it from this point is really easy. I know that it goes through this point here, right? But as I move away, it just starts blowing up and approaching. It has as x approaches the value of the asymptote, the graph has to approach the asymptote. Same thing here, right? On this side, same thing has to happen. It's going to go downward because cosecant's negative. We have these U shapes. So the two sort of disconnected U-shapes, that's the graph of cosecant. The gray graph that I did was the graph of sine, was there to kind of just help me as an aid to draw that. And to this day, if I'm drawing a cosecant graph, or a secant, I first just draw the sine or cosine that goes along with it. If there are changes in amplitude, period, phase shift, I just do all of that with the sine or cosine. Draw my asymptotes where the sine or cosine is 0, and then draw those like U shapes. Like that'll work every time. So we'll do the same thing for secant here. We'll first draw cosine, which has a period of 2 pi. Cosine starts at 1 and goes down from there. Where do I have asymptotes for this graph?
Pi over 2.
Mm-hmm.
3 pi over 2.
Yeah. Right, where cosine is 0. Basically, wherever the curve in gray, crosses the x-axis, we draw our our asymptotes there. At the peaks and valleys, secant takes on the same value. So I've got these 3 points. And then from there, I just draw my U-shapes. Now, because it's cosine, we kind of start off with these half U-shapes. We have one full U-shape in the middle, and with a half U-shape. So there is one period. If you like, you could kind of finish out, say this is minus pi over 2, draw that asymptote. Now here's the rest of cosine, and there's the rest. If you like kind of connected U-shapes, instead of having like a stray like half here, half here. Let's do one more. So we did the basic secant and cosecant. Now we'll do one. Here's 2 secant of 4x. So the first thing I'm going to start with, which is the reciprocal function for secant? Cosine. So I'm going to start with 2 cosine of 4x. That has an amplitude of 2, a period of 2 pi over 4, which is pi over 2, and there's no phase shift. So my amplitude is pi over 2. This is pi over 4, pi over 8, 3 pi over 8. My amplitude at 2. It's a cosine, and there's no reflection, right? It's not a negative 2 cosine, so it's a cosine. Starts up at positive 2 and goes down from there. I've got my cosine. That's really, I would say, the bulk of the work when you're doing the secant graph. Like, just make sure you have your cosine graph correct. And then what comes next? Asymptotes. Where do those go? Good. And then? Draw the U's. Yeah, I mean, we know that the values of the secant and secant and cosine will be the same at the peaks and valleys, and we draw our little U shapes. So, I mean, one of the bulk of the work is in graphing the associated reciprocal function, either cosine or sine, and then just remembering which one goes with which, right? If I'm going to graph a cosecant, I have to remember that reciprocal is sine. How's that? Pretty nice? Okay. I've got new set of notes. We're going to start. This next chapter is on exponents and radicals. What we're doing today is mostly a bit of kind of review. We spent some time on this last semester, but I think it's worth just sort of solidifying our skills here. Will serve us well for the rest of the chapter. Okay. So the rules in on the first page here should be familiar to us. We know that if we have the same base and we're multiplying, we can add the exponents, and if we're dividing, we can subtract the exponents. We know that if we're taking an exponential expression and raising it to a power, we get to multiply the exponents. We know, rules 4 and 5, that we can distribute an exponent over multiplication, over division. What are we not allowed to distribute an exponent over?
Addition.
Addition or subtraction, yeah. So I'm just going to kind of write this out. A plus or minus b to the n, not equal a to the n plus or minus b to the n. Right? Keep that in mind. We know that anything to the 0 power is 1 as long as the base is not 0. And we know what a negative exponent means. A to the negative n is 1 over a to the n, or if we see a negative exponent occurring in a fraction, we can kind of just move, from the top to the bottom or from the bottom to the top and change it to a positive exponent. All right, we are going to simplify some expressions. We almost always, when we do this, want to adhere to the convention of avoiding negative exponents in our final answer. What do we do? What can we do? There's more than one correct first move that we can make. I'll just say that first. But what's something we can do here?
We could distribute to the x and y.
Yeah, this first.
Yeah.
Yep. So that would look like.
X to the fourth or the second.
Great. And you got x to the fourth because we were multiplied those exponents. Yeah. And then what?
And we have to distribute the negative so we could flip the fraction.
Okay, so we're gonna do yes, but we can't do both. Like, we gotta pick one interpretation. Like, I'm either gonna distribute the negative exponent, or I'm gonna flip the fraction and write it to the positive too, right? Just don't do both at the same time, okay? You're right that it'll have the overall effect of flipping this over. If I distribute that exponent first, I have 2 to the negative 2 over x to the negative 2. And then we can flip x to the positive 2 over 2 squared. And then overall, we have x to the 6th y squared over 4. Alternatively, when we think about, like Austin mentioned, flipping the fraction, or we could have seen that as just flip that fraction over first and write x over 2 to the positive 2. I'm going to just sort of emphasize that. And basically that's just, that results from the fact that we can distribute the exponent first, and then that means we have to flip it. Obviously, we can see we're going to get the same thing regardless. Pretty good warm-up exercise. All right, what's 5 times x to the 0?
1.
Well, x to the 0 is 1. So we actually get 5. If we compare that with what we have here, this is 5x all raised to the 0 power. That's 1. The lesson here is be really mindful about what an exponent is applied to. Right? It could be really easy. It's really quick. I love seeing things to the 0 power because they're 1, and then I just get to simplify, and it seems simple, but that means it's also simple and easy to maybe overlook some details. Along the same lines, 2x to the negative 1. How do I write that without negative exponents?
2 over x.
2 over x, because that negative 1 exponent is only on the x, as opposed to in part B,
1 over 2x.
1 over 2x. Again, the moral of this lesson, of these examples here, is just be really mindful about what an exponent is applied to. You will feel urges from time to time. That's okay. Just be mindful. Don't let your urges control you. All right? Ask yourself, am I allowed to do this? We have to be really careful. Once we see, if I see addition or subtraction in an expression, I just slow myself down. Okay? I take some deep breaths. I'm trying to be in this moment and make sure I know what I'm allowed to do. All right, we have some addition. Now, I can't distribute this exponent over addition, right? Not allowed to do that. And in fact, you know, it doesn't even make sense to kind of FOIL right now because it's a -2 power, right? Like, but what I can do is say, okay, well, let's look in the parentheses, order of operations, right? Let's look in the parentheses first. We could do something with this negative exponent, right? That's 1 over b. So this is 2a plus 1 over b, all to the -2. And I'm going to just ignore that -2 power for a second and just say, well, what can I do with this expression? What can we do with this? Just forget that we're doing anything with exponents right now. If I see 2a plus 1 over b, what could we do?
Find a common denominator.
Yeah, let's do that. So the common denominator is b. So then we have 2ab plus 1 all over b to the -2. And the advantage to doing that is that now we have a fraction raised to a power, and we can distribute an exponent over division. We're allowed to do that. So this is 2ab plus 1 to the -2 over b to the -2. And then we could flip them over, right, to get positive exponents. So we have b squared over 2ab plus 1 squared. You could leave it like that, or now you could FOIL what's in the bottom if you want to. That'd be fine. Questions? Okay. We're going to do something similar here. We want to use only positive exponents in our answer. What can we do? What's one way to start? The first part is 3 over L. Great. What about the second part? Close. What?
To the power.
To the power of 2, yeah, parentheses to the +2 power. Good. What's a path forward? What's something we can do now?
Common denominator.
Yeah, but before I do that, I think that's absolutely what we want to do. I think an intermediate step before we do that is just squaring out the 2L. So 2L times 2L is 4L squared. And once we do that, now we can see this first denominator just needs a 4L. So now we have 12L minus 1 over 4L squared. You know, we have time. Maybe we'll go ahead and just do some rational exponents. Does that sound like a good idea? Jacob Van says, yes, it does. Give me 1 second. Because that way, you know, we'll do our exponents, and then the nice thing about that is then on Thursday, we come in and just do some radicals. Do you see how nice that is?
It's the long run. It's better in the long run.
Yeah.
Do I have time to get a drink?
Sure. Okay, nice. All right, so this we saw a bit in the last semester as well. So we're just going to remind ourselves what a rational exponent is. Rational exponents, a to the 1 over n just tells us the nth root. And in general, any fraction exponent, the denominator tells you what root you're taking, and the numerator of that exponent tells you what power you're going to raise it to. And as long as we're working with positive numbers in there, it doesn't matter if I raise that power inside inside the radical or raise the radical to that power. So let's say we want to evaluate 27 to the 2/3. This just says I'm going to take the cube root of 27 and then square it. Cube root of 27 is 3, and 3 squared is 9. 9 to the negative 3/2, so the first thing I'll do is deal with the negative. That's 1 over 9 to the 3/2. This says take the square root of 9 and then cube it. So that's 1 over 3 cubed, or 1 over 27. Not everything needs to be written in terms of a radical if we see like rational exponents, but if I have a number to a rational exponent, if it's a convenient base, you know, like 9, if I was taking the square root of 9, like, so that's super convenient. It's nice, it's convenient to think about it in terms of radicals. But it's also pretty common to leave things written as rational exponents. In general, in this chapter, we're doing a lot of stuff with exponents and with radicals, and often it'll instruct you leave it in exponential form or leave it in a radical form, and if it doesn't specify, I guess you could really take your pick. In this section, I'll probably leave everything in most things in a exponent form. So I've got this product that's being raised to the 4/3 power. We know we can distribute. We also have that negative power inside. I think what I would do, and I guess really it doesn't really matter which way you go about it, but I think I'm going to just throw the b to the positive 4 in the bottom first. And so we have 8c squared over b to the 4th all to the 4/3. And then I can raise, distribute this exponent. I've got a product. Overall, it's a fraction, but I got a product up top, so each one of these factors in the top and the bottom is going to get that 4/3 power. Eight to the 4/3, that's the cube root of 8, all to the 4th. The other one's going to leave in the exponential form, but I'm using radicals there because it's kind of convenient. It'll help me simplify. What about this next factor up top? What is that equal to? If I want to write it in exponential form. C to the 8/3. We get that by multiplying the exponents. We do the same thing on the bottom, multiply those exponents, we have b to the 16/3. And then the only thing left to do is to simplify that radical. So the cube root of 8 is 2, 2 to the 4th is 16, c to the 8/3 over b to the 16/3. Okay. There's a lot of different ways to start this, right? I could distribute that negative 1/2 power to everything there, right? I could take care of the negative exponent inside first. I could flip the fraction first. But one thing that catches my eye is that I have a's and b's on both the top and the bottom. So I think it might be worth it to actually just simplify what's inside, like that fraction inside first, and then deal with that negative 1/2 power after. Because we can do some canceling or use those rules of exponents inside. So I have 4. That's on top. A to the 5/6. And then on the bottom, I have a to the 2/3, b squared, b to the 1/5. Right, so all I did first was take this negative 1/5 and throw it downstairs. And this is all to the negative 1/2 power. Now I can work on simplifying the a's and the b's here. So let's work with the a's, right? If I'm dividing, we're going to subtract those exponents. So 5/6 minus 2/3, we get a common denominator of 6. So we have 5 minus 4, or 1/6. So inside I have 4 a to the 1/6 power over on the bottom we're multiplying those b's, so we're going to add the exponents. So 2 plus 1/5, we'll get a common denominator. So 10/5 plus 1/5 is 11/5, and we get b to the 11/5. This is all to the negative 1/2 power. What can we do now?
You can either flip the fraction and distribute it 1/2, or distribute it.
Yeah. So why don't we go ahead and just do the first thing? I'll flip the fraction, but again, there's options here. The more than one correct way to proceed. I'll flip the fraction over and write it to the positive 1/2. So I have b to the 11/5 over 4a to the 1/6, all to the positive 1/2. And now we can distribute the positive 1/2 power. Now we're going to just multiply the exponents for the b's and the a's, right? So b to the 11/10 and a to the 1/12. What's 4 to the 1/2 power? 2, yep. Square root of 4. And there it is. Questions? Okay. Let's try one more then. All right, so it's got some subtraction here, so I'm going to be careful. What can we do? What's a way to start?
Negative exponents.
Mm-hmm.
First one, I just do 1 over 4x over 4.
1 over what?
Well, and then to the 1/2.
Oh, 4x to the 4th, yep.
And then I'll do
And then to the 1/2, yeah, good. Yep, and then?
minus 3 over.
Good. Great, yeah. So that negative 3 power over there is only on the x, so the 3 stays up top. What now?
And then distribute that to the 1/2.
Yeah. So we got 4 to the 1/2, x to the 4th to the 1/2, and 4 to the 1/2 is again 2. When I multiply the exponents, x to the 4th to raise to the 1/2 power, that's x squared. So we have 1 over 2x squared minus 3 over x cubed. And where can we go from here? Yeah. Right, so the first fraction needs to pick up an x. Second fraction needs to pick up a 2. So we have x, on top we have x minus 6. On the bottom, 2x cubed. Doesn't it feel good that we got through the rational exponents today? You guys are pretty stoked about it. The quiz will still just cover up through the integer exponents. That's what's covered on the practice quiz. And on Thursday, we'll come to class and jump in with new material. We'll work with radicals first. Then we'll stop and I'll take questions that you might have on the quiz material, and then we'll do the quiz. We have recitation today at 11. I've got a practice quiz. I've got the practice quiz that I can hand. I've got them copies right here, so I can hand those out. And I'll be in room 212 at 11 for folks who want to work on it there. Also, you might choose to use part of recitation to get your problem that's been assigned, so you can get some points back on the test. You could work on that problem there. That would be a good use of that time as well.